We are the Space Cowboys, Oklahoma State University's NASA Suits Design Challenge team, and this is a human-centered computing design of mixed reality suits interface. In this project, the focus was on the creation of mixed reality-based cyber-physical user interfaces for the Exploration Extravehicular Mobility Unit for the HoloLens 2 platform. During the design of the user interfaces, the team focused on the adoption of systems engineering processes, while emphasizing agile software development approaches and human-centric computing principles. The IDEF Zero modeling method has been used to highlight the adoption of systems engineering, while delineating the functional flow to various activities. UML-based sequence and activity diagrams were used to model temporal interactions and functional calls between the software objects used to build the UIs. A unique aspect of these cyber-physical approaches that the team proposed is the adoption of human-centered computing principles to help design user-friendly and human factor-oriented UIs to support the cyber-physical activities. An iterative design process was adopted. The initial design layout involved proposing several menu-based alternatives and layouts, which were refined based on user-friendliness and cognitive load.
One of the most important objectives of the NASA Suits project was to guide the users between EVA assets and designated geology sites. Our approach used an A*-based algorithm and data from the HoloLens 2 to guide users around obstacles. The HoloLens 2's spatial mapping recognized real-world surfaces in the environment, which would help the users navigate and avoid obstacles in real time.
We created our science sampling menu as a toolkit to aid the astronauts in their sample recollecting missions. Our science sampling menu has 5 elements: checklist, voice note, take picture, record video, and sample collection. Before entering the mission, astronauts will be able to create a checklist through voice recordings that they will be able to access at any given time. They also have the ability to record voice notes of the samples that they are looking at, take pictures, and record videos. Once they are done with these tasks, they are able to collect the sample with the tool of their liking.
The program uses network connections to retrieve vital data that an astronaut would need during an EVA and implements a fast error detection system to display unobtrusive warnings to the user. The amount of information visible can also be adjusted to fit the needs of the user. The airlock menu displays a 3D model of an airlock with interactive buttons to show and tell the astronaut about proper airlock procedure. Interactive tutorials can feature 3D models, text, and voice narration to convey important information while leaving the user's hands free. Our outreach includes a K-12 STEM program featuring a non-immersive version of our headset display for 10th, 11th, and 12th graders, with more K-12 outreach planned for the future. We've also submitted papers in FIE publications and AIAA. Our UI is still in early stages of development, and there are further improvements to be made with further HCI and functional testing. With this in mind, the foundation has certainly been set for an interactive UI system that the next generation of astronauts can use to better navigate complex tasks amongst the stars.